Hi there, welcome to my channel. In this video, I'm going to discuss about the solution for word ladder problem. Let's look at the problem description. We are given begin word and end word and a dictionary of words, and we have to return the number of words in the shortest transformation sequence from begin word to end word. If there is no such sequence exists, then we have to return 0. So the conditions here is every adjacent pair of words differs by a single character. For example, transformation from the word hit to the word hot is a valid transformation because it's differ by only one character. All the intermediate words as well as the end words are present in the word list, and the begin word is not present in the word list. Okay, so let's take a look at the example 1. So in this case, the begin word is hit and the end word is cog, and the word list is hot dot dog lot log cog. If we look at it, this is the begin word. From here we can transform into the word hot. From there we can transform into dot because h and d, these two words differ only by one character, and then from dot to dog because these two are differing in the second character in those words, and dog to cog. So totally there are 5 words in this sequence, so we have to return 5. And in the case of example 2, we can transform from hit to hot, hot to dot, dot to dog, and dot dog to log, but we cannot reach the end word cog, so that's why we have to return 0. So in this case the end word is not present in the word list. In this case the end word is present in the word list. Okay, constraints are the begin word length is ranging from 1 to 10, and the begin word and the end word lengths are same, and the number of words in the word list is ranging from 1 to 5000. And one more thing is the length of the words in the word list are equal to the length of the begin word length. That means all the words in the word list and the begin word are all of same length. Okay, and the begin word will not be equal to the end word. Okay, they are unique, and also all the words in the word lists are also unique. Let's look at the approach to solve this problem. So the input given is the begin word is hit and the end word is cog, and the word list has 6 words which includes the end word. So we need to find the number of words in the minimum transformation sequence. In this case it is 5. We can model this problem as a graph problem. For each word, the next possible words are all its neighbors. For example, in the case of hit, it has only one neighbor because only one word is differing by one character, hit and hot. But in the case of word dog, we can see 1, 2 and 3. 3 words are differing by one character. Dot is differ by the last character, and the log is differed by the first character, and the cog is differed by the first character. So for the word dog, dot, log, cog are valid neighbors. If we represent the input data as a graph, we will get this graph. Okay, so the word hit has a neighbor hot, the word hot has a neighbor dot and lot, the word dot has a neighbor hot, lot, dog. So like that, for each word we connect who are all the neighbors. Okay, we have to find the minimum number of transformations, that means the shortest path from one word to the other, right? So in this case we can do breadth first traversal on this graph. That gives the shortest path from the starting node to the ending node. Okay, so in this case the path will be hit, hot, dot, dog, cog. So the approach is we have to do the breadth first traversal on this graph. Okay, so that's what I have listed here. So the words transformations can be viewed as a graph, and each word is treated as a vertex, and the neighbors are connected, and each word is connected to 0 or more words depending on the words that are differing by only one character. And if we do the breadth first search, it will give the shortest path from the starting word to the ending word. Let's look at the flowchart. Input for this procedure is the begin word, end word, and the word list. Okay. So first thing we have to do is add the begin word to the beginning of the word list. Okay, because the index 0 is for the starting word. So this will simplify the logic during the breadth first traversal. Okay, so that's why we have to add the begin word to the beginning of the word list. Then we have to initialize the visited array and the word count array and the queue. So these three data structures are used during the breadth first traverse. The visited array will the index in the visited array indicates whether the corresponding word is already visited or not, and the word count indicates from the starting word to the current word how many number of the words present in the transformation sequence. That information is kept in the word count array. This queue always hold the next level nodes in the during the traversal. And then we initialize the sequence variable to 0. If we find the transformation sequence that reaches the end word, then this will be updated with the number of words in that sequence and return back. Next, we will add the index of the begin word, which is 0, to the queue and mark that vertex as visited, and we initialize the word count for the start vertex with 1. Then we enter the outer loop. This loop will run as long as some elements in the queue. Each iteration we dequeue the first element from the queue and get the list of neighboring vertices for that dequeued element. Then we enter the inner loop, which actually visits the neighbors of the current node, and it will check whether the dequeued neighbor already visited or not. If it is not visited, mark this node as visited, then add 1 to the word count of the current node and assign that to the word count of the neighbor. Okay, then add the neighbor to the queue. After this, we check whether this neighbor is equal to the end word. That means we reach the end of the transformation or not. So if it is yes, then we assign the word count of the end word to the sequence count variable and return. Otherwise, we process the next neighbor. Once all the neighbors are processed, then we go and process the next level elements in the graph. Okay. Once the queue becomes empty, then finally we return the value sequence count. So if during the traversal, if we reach the end word, we update the word count. We will have the number of words in this transformation sequence. Otherwise, we will have the 0 as the sequence count, and we return that. Let's move on to coding. First, I define the constant for visited and not visited state. Next, I add the begin word to the beginning of the word list. Then I initialize the count variable with the length of the word list. Then I initialize the visited array to keep track of which node is visited, not visited. Then the word count array. This will keep track of the number of words to reach the current word from the begin word. Then I initialize the queue This will hold the next level elements to be processed during the breadth first traversal. So first I initialize with the index 0, that is the begin words index, and then I mark that word as visited. Then I initialize the word count of the begin word as 1 in the word count array. Then I write the outer for loop. This will run as long as there is an element in the queue. So each iteration it dequeue the first element and assign that to the current index variable. Then get the current word present in that index. Next I will get all the adjacent words that are differing by one character from the current word. I call the get next word index function, which will return the indexes of all the words which are differing by one character. Then I iterate over those indexes in the inner for loop. In each iteration I check whether that next index is already visited. If it is not visited, then I mark that as visited. Then I add the next index to the queue. Then I update the word count of the next index by adding 1 to the word count of the current index. Then I check whether the word present at the next index is equal to the end word. If so, we reach the end word. So I return the word count of that next index. Then finally I return 0. This is for the worst case. If the end word is not reachable, then 0 will be returned from this function. Next I am going to write the get next words index function. This takes the current word and then the word list. It returns a slice of int. First I initialize the next words index slice with the empty slice of an int, and then I iterate over the word list and compare each word with the current word. If they are differing by only one character, then I include the current index into a next word index slice. And finally return that slice. Next I am going to write the is differ by one character function. So in this function I compare the first word and second word and keep track of number of characters they are differing from in the count variable. If the current characters differ, then I check whether the count is already 1. In that case it's going to differ more than 1, so I return false. Otherwise I increment the count, and finally I return the boolean value of the expression count is equal to 1. Next I'm going to run the test cases. All the tests passed. Next I'm going to submit this program. Cool, this program is accepted. Next, I'm going to do the code walkthrough with sample input. Let's do the code walkthrough for this input. So the begin word is hit and the end word is cog. That end word is present in the word list, and the expected output is 5 because the number of words in the shortest transformation is 5. So this is the path. Okay. So first we add the begin word to the beginning of the list. So hit will be at index 0. Okay. So after adding the begin word, so the index 0 has the begin word and the index 6 has the end word, and the intermediate words are in between. And the count is initialized with the length of the word list, that is 7. And then we initialize the visited and the word count array. Next, we add the index of first word in the queue. So now queue has 0. We mark that vertex as visited. Okay. And then the word count is set to 1 because in this transformation the number of words currently 1. Then we enter the outer for loop, which runs as long as there is an element in the queue. Okay. So in this case there is one element, so we are entering the first we dequeue the element from the queue. So the current index is initialized with the first element in the queue, which is 0. Then the queue becomes empty and the current word is the word present at the cur index in the word list, which is the word hit. Okay. So once we initialize that, then we get the next possible list of words which are differing by only one character. So we call the get next words index function, which will go over the words in the word list and return all the words which are differing by one character with the current word. Okay. So in this case only one word is differing by one character, which is the word hot, that is present in index 1. So the get next words index function returns a slice of int with only one element, that is index 1. Okay. Then we iterate over that next words indexes, and for each index in that list we check whether that particular index is visited already or not. If it is not visited, then we mark that as visited, and we update the distance of that word by adding its previous neighbor. Okay. So in this case the word hit is the previous neighbor. So the word count of this word plus 1 will be the word count of this word. Okay. So 1 plus this 1. We update the word count for the word hot. Okay. Then we check whether that neighbor word is equal to the end word. In this case it is not, because the end word is cog. Because we process all the elements in the neighbors list, then we come out of this inner loop and then we start processing the elements in the next level. So this is the level 1. Okay. So now the outer loop iteration 1 begins. Then at that time, so in the outer loop iteration 1, we dequeue the element from the queue, which is the index 1, and then we find the word associated with that index, that is hot. Okay. Next we make the get next words index function, so that returns 2, 4. So 2 and 4 are returned, which are these two words are differing by one character from this word. So hot and dot h d and hot and lot h and l. So we get 2, 4 as the next possible transformation. So then we enter the inner loop, we process the index 2 and then the word at index 4. Okay, so we check whether this vertex is visited already or not. It is not yet visited, so we mark that as visited and update the word count by adding the 1 to the previous neighbors. Technically it's a parent of, in the BFS tree this will be the parent of this node, so the word count of this parent plus 1 will be assigned as the word count of this vertex. So 2 plus 1, 3 will be updated at index 2 in the word count array. Okay, after updating that we add that index to the queue. So the queue now has 2. Okay, so now we process the index 2. Next we will be processing index 4. So the inner loop iteration 1 process the index 4. We check whether the vertex 4 is already visited. It is not yet visited. It is not yet visited. So we mark that as visited and then we update the word count of that vertex by adding 1 to its parent, which is at index 1. So 2 plus 1, 3. So the word count of this word is 4. Once those two elements are processed, then we come out of the inner loop and then we go ahead and process the next level elements, which is at level 2. So that is these two nodes. Okay, so we dequeue the first element in the queue and assign that to the current index and get the current word associated with that index, which is dot, and we get the next possible words that are valid transformation from that word. Okay, so we get, I think it's supposed to be 1, 3, 4. Okay, because for the word dot 3, 4 and 1, these three words are differing by 1 character. Okay, though this word is already visited, these two are already visited, we still return that as a possible transformation. So now we have 1, 3 and 4. I haven't shown the block for processing the node 1 and 4 because they are already visited. So now this will probably in the iteration 1 and iteration 0 and iteration 2 takes care of processing the node 1 and 4. Okay, so the vertex 3 is processed in this iteration. So we check whether 3 is already visited. It is not yet visited, so we mark that as visited here and we update the word count by adding 1 to its parents, which is 2. So 2's word count is 3. So 3 plus 1 is, 3 plus 1 is 4. The 4 is assigned as the word count for the word dog. And then 3 will be added to the queue. Next we enter the outer loop iteration 3 to process this level. Okay, so in this queue, in the queue first element is 4. So we dequeue that element and assign that to current index and get the next word indexes. So for the 4, the possible words are located at index 1, 2 and 5. So that's why the next word index we get is 1, 2, 5. And in the iteration 0 we process the node 1. We check whether it is already visited or not. We see that is already visited, so we skip that processing. So that's why in this iteration we don't see any change in the visited and the distance data structure. And in the iteration 1 also there won't be any change because node 2 is already visited. And in the inner loop iteration 2 we visit the node 5 which is not yet visited. So we mark that as visited, and then we update the word count for that index by adding 1 to its parents word count, which is 3. 3 plus 1, 4 is assigned to index 5. Okay. So now then the index 5 is added to the queue. So now we have 3 to 5 in the queue. Then we complete the outer loop iteration 3. Then we go ahead and process node 3. So we dequeue that from the queue, and the current index is 3, and the next possible words are located at index 2 and index 5 and index 6. Here also it should show. So this is for processing the node 2 which is already visited. That's why we do not see any change in the visited and the distant data structure. And this one we can say iteration 2, inner loop iteration, that process the next word index 6. Okay, so that gets added here. So when we come to the inner loop iteration 2, we process the next index 6. Okay, and we check whether that is already visited. It is not yet visited, so we mark that as visited, and then we add 1 to its parent which is at index 3. So the word count is 4. 4 plus 1, 5 is assigned as a word count for the word at index 6. Okay, so once that is done, we check whether the word list at index 6 is the end word. In this case, it is the cog is the end word located at index 6. So we assign the value 5 as a return value, and we return that as an output. So we are returning 5 in. So that is an expected output. Next, I'm going to do the time and space complexity analysis for this solution. Let's do the complexity analysis for this input. This has begin word, end word, and the word list. So in this case, the word list contains the end word. So if we include the begin word also to the word list, totally it will have 7 words, and the expected output is 5. So in order to determine the sequence of transformation from the begin word to the end word, we have to traverse at most all the nodes. The breadth first traversal algorithm processes each node at most once. So the total time complexity is, in this case, it's 7 processing. So for n number of words, it will be order of n. The space complexity for this algorithm is order of n, because we need to allocate space for the visited and the distance array, which are equal to the size of the length of the word list. Okay, so in this case it is 7. So if we have n number of words, then we have to allocate space for all the n elements. So that's why it is order of n. And we also use space for the queue, but this depends on the degree of maximum degree of the node present in the graph. So in this graph we have a maximum degree is 3, but if we have a graph where all the words in the word list differ only one character from the begin word, then in that case the degree will be n minus 1. So the space complexity for this algorithm is order of n. Thanks for watching this video. Have a great day.